Alright, in this next problem we're looking at how to calculate entropy change for an idle gas such as air. Problem says air is compressed from an initial state of 100 kilopascal and 17 degrees Celsius to a final state of 600 kilopascal and 57 degrees Celsius. Determine the change in entropy of the air. So in this case, our system is air in a compressor, which air is an idle gas, and a compressor is an open system. For the conditions, we don't really have any other conditions except the fact that it must be a steady flow compressor, because all of the compressors that we studied in this course are steady flow. Other than that, it's not constant temperature, not constant pressure. For the compressor, we don't need to write the first law necessarily, but if we did, we could assume that Q is equal to delta KE is equal to delta PE is equal to 0. Those are our typical conditions for a compressor. Then for the properties, we have pressure at the inlet is 100 kPa. Temperature at the inlet is 17 degrees Celsius or 290 Kelvin. And the final state, which is the exit state, P2 is 600 kilopascal. And the exit temperature is 57 degrees Celsius or 330 Kelvin. Alright, now we're ready to go ahead and solve. We're asked for one thing, the change in entropy of the air. Alright, so as we're looking for the change in entropy of the air, we think about what type of substance we have. In this case, we have an idle gas, air. So whenever we calculate delta S of an idle gas, we use an equation instead of the property tables. So first thing is we just need to look up one of our equations to calculate delta S of an idle gas. So we have two ways that we can calculate it. We can calculate it as C sub V natural log T2 over T1 plus R natural log of V2 over V1. The other equation we have is delta S is equal to C sub P natural log T2 to T1 minus R natural log P2 to P1. Now we can use either one of these equations at our discretion. We just want to use whichever one is simpler for what we know. In this case, we know the initial temperature and pressure, and we know the final temperature and pressure. So pretty much everything in this second equation is known except for R and C sub P. So we need to calculate R for air. Take universal gas constant, divide by the molar mass. So the molar mass of air, if we pull it up in our properties packet, molar mass for air here we can read off as 28.97 kilograms per kilomole. So going over to our calculator, first of all I'm going to clear everything out from the last problem. Alright, hang on. So MATLAB is deciding to go slow still. It's not going to like this because I put CLAER. So it's going to spit back an error message. Sorry, I still apologize for MATLAB and my computer in general being slow today. Okay, well, back to the problem for a minute while this clears up. Also, we need to get specific heat, average value between T1 and T2. So from the properties packet, T1 is 290. You can go to the end of the properties packet for specific heat values. So C sub P at 290, we would have to interpolate here between 250, 300, 1.003, and 1.005. So C sub P at 290, we're interpolating here 250, 290, 300, 1.003, and 1.005. We'll get that number here in a second. C sub P at T2, T2 was 330. So at 330 we're interpolating between 300, 350, 1.005, and 1.008. Alright, so now we just need our calculator to work. Here we go, looks like it's back up. This time I'll type in clear correctly. Clear all the variables that were saved as something and then clear off the screen as well. So first thing we wanted to do was we wanted to calculate R for air. So R for air, we would use the universal gas constant, 8.314 in SI units, divided by our molar mass, which was 28.01. Or actually, let me check that again. R for air not 28.01, 28.97. Alright, so there's R for air, 0.287. And then for specific heat at 290, we'd interpolate 250, 290, 300, 1.003, and 1.005. So there's C sub P at 290. Hang on, I have to change my folder to do interpolation. Sorry, trying to bring up the last function call. Okay, I wish MATLAB and my computer were not so slow. This would be a lot quicker problem. Alright, finally maybe we have something. Okay, here's C sub P1, 1.0046. And for C sub P2, we need to interpolate. 300, 330, 350, 1.005, 1.008. So C sub P2, we get a value of 1.0068. Alright, now we can get the average specific heat value. So the actual value we're going to plug in for C sub P, we take the average of C sub P1 and C sub P2. We're going to be actually plugging in 1.0057. Okay, so now with our equation, everything is known. C sub P, R are known, and then T1, T2, all of that is known as well. So last thing to do is just plug this in, and we'll get delta S, little s, is equal to C sub P times natural log of T2, where T2, we need to look at it again, T sub 2 is 330, divided by T1, 290, then minus R times the natural log of P2, 600, divided by P1, 100. So our change in specific entropy is going to be negative 0.384. Alright, so a couple things here. First of all, the sign of delta S, or the units actually. Units here are specific heat units for this term because natural log, the kelvins cancel out. Also, it's units of R here, the natural log units of pressure will cancel out since there's a division. So it's just the units of C sub P and R, which are kilojoule per kilogram times Kelvin. So that's for the units. For the sign, it's okay that we get a negative sign for delta S. It's just not okay to get negative sign for entropy generation. The last thing is the question technically asked, what is the change in entropy of the air? Alright, the change in entropy, that's capital S. And all we found was the change in specific entropy. But it doesn't look like we have enough information, so I think there's probably a typo in this problem statement. It says we do have the pressure, we have the temperature at the original state, but even using the idle gas law, we don't know the volume, so we won't be able to determine the mass. So let's just say that we change this to determine the change in specific entropy of the air. So we'll just make our little change right there. And instead of this looking for delta S, we're just looking for delta S lowercase. So the number we found using the idle gas delta S equation is right here. And then for the sketch, we're sketching everything on a TS curve in this chapter. So first of all, we would sketch in some pressure lines. So initial pressure, or actually doesn't matter whether it's initial or final, inlet or exit, the higher pressure is 330 and the lower pressure is, higher pressure is 600, lower pressure is 100. Alright, at 600 kilopascal, we have a temperature of 330, so it's also the higher temperature at state 2, 330, and T1 has a lower temperature, 290. So let's sketch actually state 1 first. State 1 is at 100 kilopascal and a temperature over here of 290. So we want to sketch state 2 relative to state 1 at least correctly. So what that means is we want to show the specific entropy, is it bigger or smaller than the specific entropy at state 1. So we got a change in specific entropy of negative, meaning that S2 is less than S1. So whenever we sketch our point for state 2, we need to make sure that it's to the left of state 1. That means we had a negative change in specific entropy. And then we can label our temperature over here, 330. And in between, we didn't have any sort of special process, so we'll just draw some dotted lines. So the main things we were covering in this problem, how to calculate delta S of an idle gas. For an idle gas, we always calculate delta S using one of the two equations that I gave you in the notes. The first one looks like this, with specific volume and temperature. The second one looks like this, with pressure and temperature.